PhD student in the Department of Energy Resources Engineering, and I'm in the Geothermal Research Program, which is headed by my advisor, Roland Horn. And I'll be talking about my research doing modeling of enhanced geothermal systems, and I'll describe what that is. So first, this is the Stanford Geothermal Program right now. Program's about 35 years old. This is our cast of characters right now. I think we have one new student this year I think he's here somewhere. Maybe, I don't know. And we do research on a variety of topics, all broadly characterizing flow in fractured networks. So briefly, what is geothermal energy? When you have a place in the subsurface of the Earth that has a high temperature, and by high temperature I mean 150 degrees C or more, it's possible to drill a well that's pretty deep, and by pretty deep I mean several thousand feet, and produce water or steam to the surface and use it to produce electricity. And this picture shows that usually you actually re-inject your cooled water after it's been circulated through the power plant. So what are some of the advantages and disadvantages of geothermal? One is that it has a minimal environmental impact. The emissions from a geothermal plant are either zero or very small, depending on the type of power plant, and the surface footprint is minimal. It's also a baseload source of electricity, so it's available at a continuous rate 24 hours a day. And it's economically viable now, and it has been for decades with current technology. So there's one big limitation to geothermal, and that is that you need a happy confluence of geological conditions to produce geothermal energy. You need the Earth to be hot within a reasonable drilling depth, and you need permeability. So you need the ability to flow a high rate of fluid into your wellbore, because if you drill a well and it's hot and you can't produce enough water out of that well, then it's not economically viable. These are locations of geothermal fields around the world. These are the largest. You can see that they're generally, for the most part, at plate boundaries where the Earth is going to tend to be hotter. And there's about 10 gigawatts of installed electrical capacity around the world. So that's about enough for about 10 million Americans. So that's not negligible, but it's certainly small compared to the size of the global energy infrastructure. And this is overall production of renewable energies in the U.S. from 2004 to 2008. And what you can see if you look at the geothermal in blue is that it really hasn't been trending anywhere. It's basically been flat for several years. And that's because there really haven't been any discoveries of good geothermal fields in the U.S. for a while. Comparing that to the size of like wind and solar, you can see that geothermal, there's still a lot more geothermal electricity produced than solar. And in 2004, wind and geothermal were about tied, but since then, much more wind capacity has been installed while geothermal has been flat. So, setting the stage for what is enhanced geothermal systems. So like I said, you need both heat and permeability, the ability to flow water at a high rate. So it turns out that a place in the Earth that's hot enough to produce geothermal electricity, that is 150 degrees Celsius or hotter, is available within a reasonable drilling depth across much of the surface area of the Earth and of the United States. So the average geothermal gradient is about 30 degrees C per kilometer. So on average, if you drill down 5 kilometers, you'd get to about 170 degrees Celsius. So the problem is if you drill a deep well, often you'll hit a really impermeable rock. Usually it's granite. And so you're not going to be able to produce a high flow rate of water to your well. So the idea is to do what's called fracture stimulation. And so fracture stimulation works by injecting water at high pressure. And there are two things that might happen. One is you might create new cracks in the rock. So you actually pop open the rock, you inject it a pressure that's greater than actually the weight of the Earth above you, and you can propagate a fracture into the rock away from your wellbore, and that fracture is like a conduit for flow. So that is where the fluid flow would be localized. The second thing that might happen is you might trigger slip on a pre-existing fracture. So in granite, there's almost always pre-existing fractures, and they would like to slip because they're under a lot of stress, but there's friction resisting that slip. So when you increase the fluid pressure, you weaken the strength of friction, you can allow them to slip, and when they do, it increases their permeability, the ability for water to flow through those cracks. And so those are the two possible things that can happen in fracture stimulation. So you can do that, and you can drill into this really impermeable rock, perform fracture stimulation, and dramatically increase the flow rate you can get from that well, and the idea is to make it economic. So this idea has been around for several decades, and there have been many projects originally funded by governments, and currently there are some commercial projects in Australia and the United States and Europe, although it still hasn't been shown yet that it can be done economically, so that's why it's a research topic. And this is just to illustrate kind of the potential scale. So this is a map of the temperature of the U.S. at 4.5 kilometers of depth, and everything that's yellow, red, or orange, it's hot enough at that depth to produce geothermal electricity. So what you can see is that that's a pretty significant percentage of the surface of the United States, and that the heat in place at that depth is huge compared to the amount of primary energy that we use in the country. So at least theoretically, if we were able to achieve high flow rates through EGS wells at depth, and we were able to do it at a high enough flow rate to justify the cost of drilling, then this is kind of the holy grail of geothermal, and we could produce a very large amount of geothermal. But I would also point out that there's a spectrum of economic opportunities, so that's the best case scenario. But the lowest hanging fruit for EGS is to take a well that's been drilled at a pre-existing geothermal field, but didn't have a high productivity, and you could stimulate it. So clearly that's kind of how EGS needs to get started. So traditional hydraulic fracturing, the idea is, this is really the way they think about hydraulic fracturing in oil and gas. So they've been doing it in oil and gas for several decades. And usually what happens in oil and gas is they create this new fracture. So they'll inject this water, it'll create this new fracture, it'll grow away from the wellbore, and then what they do is they pump in sand or some other granular material so that when they stop pumping and the fluid pressure goes down, the crack can't close back up. It closes back onto that sand, and it's held open. That's a conduit for flow. So that's a pretty well understood process, and it's been around for many decades, and it's also well understood because the oil and gas industry is well funded, and so they've done a great job of researching it. Although surprisingly not that great of a job. But in EGS, what we're usually doing is we're causing slip on pre-existing fractures. So this is, the difference is that we're in a different type of rock. We're usually in granite as opposed to a sedimentary rock. And it turns out that it generally behaves differently. So there's always these fractures in granite. We're gonna cause slip on these fractures, and it's gonna increase their ability to flow. And so these are just some pictures from a real EGS project in Europe. And on the right, what they did is they had drilled a circular wellbore, and they put an instrument in before and after the stimulation, and they could literally see that the shape of the wellbore had been altered by the stimulation. So what is my research? I'm working on development and application of computer modeling tools, really software code, that can describe the physics of when you're doing hydraulic stimulation in EGS and causing slip on pre-existing fractures. And so the advantage of that, of course, is to actually go out and run a real life experiment. Costs millions of dollars. You have to drill the well and hydraulically stimulate, and that's very expensive, and it's going on around the world. But you could do a lot more if you could run numerical experiments, and that's a lot cheaper. So we're trying to develop, we're writing code that does that type of modeling. So the first is we're trying to understand the physical processes, what's taking place, and what's causing the observations we're getting. And then the goal is to design optimization strategies. So looking at things like, even though we're talking about granite, not all granite's the same. So identifying the optimal geological conditions, wellbore orientations, the way that the simulation is designed, and to try to do that to improve what really matters, which is your economic parameters. So the research problem in EGS, I think, is to make it economic. So to improve your flow rate, and also to look at the sustainability of the resource and make sure that you're going to be able to produce a high temperature fluid at a high flow rate for a duration of time that pays off the well. And then the final thing I should mention is when you trigger slip on these fractures, sometimes it triggers little micro earthquakes, and the largest are magnitude 3 or so. So that's actually strong enough to be felt at the surface of the earth, which is very frightening if it happened to occur under a city, obviously. So that's a big concern for this technology. And of course, it's important to consider, well, could we trigger a bigger earthquake? And so it's never happened, and I don't think it should happen, but I think it in the right place it could happen. I think if you try to hydraulically stimulate the San Andreas Fault, you might trigger an earthquake. So it's very important to do seismic hazard analysis before any of these sorts of projects, and they're usually done in remote areas. And so it's necessary to have a really good modeling and physical understanding of how you're triggering earthquakes if you want to be able to accurately assess the hazard of potentially causing a seismic event. So just to kind of discuss some of the things that issues when we're doing modeling. We're doing fluid flow and fracture networks. So if it's in granite, there's very little fluid flowing through the solid granite. It's a very impermeable rock. So we're doing fluid flow through networks, and we understand the physics of how fluid flows through fractures reasonably well, but what we don't know very well is what's the geometry of the fractures. If you're kilometers below the surface of the Earth, you can't just go look at them, and it's surprising how difficult it is to actually gather data on the geometry of these fracture networks. Oil and gas, they do a pretty good job of imaging the subsurface, but we're in a different type of rock, and it's much harder in granite than in sandstone layered sedimentary rock. We have to deal with a lot of stress and strain issues. So if a fracture is slipping, what's causing it to slip is the stresses on that fracture, and when it slips, it's going to change the stresses in the rock around it. There are other things that can affect the stress in the rock. We're injecting cold water into a hot formation, so when the rock cools down, it contracts, and that changes the stress. And also there's poroelastic effects. So when you're putting water into the pore space of a rock, it actually can basically swell a little bit, and that changes the stress state. So these are things I have to worry about. Also, friction evolution. So an earthquake, what it really is a situation where friction weakens and then re-strengthens very rapidly on a fracture. So we actually have to model friction itself on the fractures. And then another really, I think one of the coolest things about reservoir engineering in general is dealing with uncertain and incomplete information. And we have poor information about what the fracture networks looks like. We can observe the fractures at the wellbore. We can try to locate these microseismic events, but that data is incomplete, and so it's a very important issue to integrate our incomplete data and try to make a realistic model. And finally, computational efficiency. That's something I have to worry a lot about. I have to write a model that can run in a reasonable duration of time. So here's just some pictures to kind of illustrate the sort of thing I'm talking about doing. So if you look at the upper left, that's a map of the blue lines are fractures. They're the pre-existing fractures, or the thick blue lines are the fractures that have slipped, so their permeability has been enhanced. The red line was an injector, so that was a model where we injected from that red line and triggered slip. And so the idea is to be able to develop a realization of what the permeability map looks like after the hydraulic stimulation. You could do that to project future performance. For example, if I have an injector and a producer, if I inject a bunch of cold water, I'm going to start cooling down the formation. How quickly until I start producing cold water? That's a very important question. Also, trying to optimize your flow rate, things like that. And so you can also predict the locations of seismic events, or you might go backwards and have the locations of seismic events and use that to constrain your model, and then predict magnitudes versus time. So I have two movies I'm going to show. And I think, all right, so this is injection into a single isolated fracture. So what this is a 500 meter, it's a two-dimensional simulation, or it's a linear fracture. What we're doing is I'm injecting into the middle. The x-axis is distance, and then the y-axis and these boxes are different properties. So if you look at the upper left corner, that's the slip velocity. And so what's happening is it's a log scale. That's actually earthquakes that are nucleating and then propagating along the fracture. So you see I'll run it one more time. If you look at the upper left corner, when the velocity goes up and then you see those waves of velocity, that's actually an earthquake nucleating and then propagating along the fracture. And so I've borrowed a lot of stuff from geophysics. They do earthquake modeling in geophysics, and I'm using that type of modeling in this approach. So, and then there's other things in this movie, like the permeability is evolving, the fluid pressure is propagating out from the injector well. The second movie here, now this is a fracture network, and so those three solid black lines. First, I'm going to inject into the upper left fracture, and then I'm going to inject into the middle fracture, and then into the bottom right fracture. So the color is the fluid pressure. So the red lines are are higher fluid pressure. The blue lines have lower fluid pressure. And so this is just showing fluid pressure, but this full model is calculating the stresses. These fractures are slipping, changing the stresses around them in a heterogeneous way. And so I could also develop a map of the permeability that resulted from this injection experiment. And so what I'm doing right now is making this a three-dimensional version of this. And actually, the challenge is not writing a three-dimensional model, it's making it efficient. And so that's what's occupied a lot of my effort. But I'm almost there, actually. So I just want to conclude by kind of talking about why I'm interested in this and why I enjoy working on what I'm working on. It's a really complicated, multidisciplinary problem, so I have to deal with geology, geophysics, reservoir modeling, computer modeling, And I'm really fortunate that, of course, Stanford has strong departments in all of those areas. And so I've benefited a huge amount from being able to go to professors, even in a different department, and saying, I'd like to learn about how to model an earthquake. Can you help me out with that? And they're more than happy to do that. And that's a really great thing about Stanford in general, but it also, I think it makes it a really interesting problem. And of course, I think that EGS at least has the potential to have a really big impact on how we produce energy. But there's clearly research problems that have to be overcome. And also, from my point of view, it's a pretty undeveloped field in terms of the work that people have done on modeling of EGS stimulation is amazingly undeveloped. And so it's actually a situation where I feel like an individual like me can make a contribution to that. And that's why I even started the PhD, is I looked at what people had done and said, wow, there's so many opportunities to do better. So that's why I'm excited to be working on it. And finally, it's also nice that the work that I'm doing has applications in other areas, not just EGS, but induced seismicity in general. So other things that people do where you take fluid in or out of the earth can trigger earthquakes. And also, natural gas hydraulic fracturing is also very closely related to the type of modeling I'm doing. That's been getting a lot of negative press recently, but it's a very important part of how we produce energy as well. So anyway, that's why I'm interested in what I'm doing, and that's it.